Good, it started recording. Uh, Good morning. Looks like we might have like a holiday on Monday or something, and some people wanted a 5-day holiday instead of just a 4-day. Of course, they probably don't have classes on Friday. That's fine. I wanted to, again, sort of reiterate on attendance. Uh, the main reason for attendance policies is because the system is afraid that if you aren't in class, you're out doing terrible things, stealing, whatever. I don't know, something like that. My grandparents went through Indian boarding school, and they were sent out because, again, to kind of destroy their culture, but also they were afraid if they left them to be, they'd do terrible things. So it was sort of. So to me, attendance policies are all about government control or somebody's control. Maybe in high school you need to do that. I still don't think it needs to be done in high school, but certainly at college level, we're adults. You're pursuing knowledge for your knowledge's sakes. So let's give you the freedom to be human, right? So, but I do appreciate each of one of you that are here, because I could be sitting at home in my office and doing this through Zoom, but those are not as live as when I'm in the class. And even if you're not asking questions, I can sort of see your faces. I need to get my prescription for my eyeglasses updated because I can't see close and far. So I decide to see close. So all your faces are a little fuzzy. I do kind of see where your eyes and nose and stuff is, but everything's a little blurry. But it's still, I get some feedback from y'all. I can see when you're smiling. I can see you either got the joke, maybe it was corny, but you smiled anyway, or maybe you didn't, and then I know, okay, throw that one away. Let's do something else. So it's great. I appreciate you coming when you need to. However, I also appreciate those who maybe have a 45 1-hour commute, and maybe this is their only class, and so they're spending 2 hours to get to a class where they spend an hour. Maybe if we can use our technology and they can view the recording, they actually get more done and they actually learn more deeply. Because that's what this is about. Is, again, remember, I want you to be thinking about what is skillful for you. Okay, so don't worry about if you're here or not here. Just worry about, are you learning the content or not? Are you finding a way to do that? And we'll be good. So I'm going to share some things with you here about our homework and our course. First of all, I want to apologize a little bit. This is my view of it, and notice I don't always see this, but what comes up first is the master course. So actually, I was changing the due dates in the master course, which don't tell anyone else because I'll get in trouble. But I'll just tell them that's what I did. I'm supposed to only change my course. Everyone else copies off the master, so they've already done that, and it's probably not. It shouldn't be affecting anyone. If it was, they probably would have got an announcement. So, about a day ago, I realized I hadn't been updating the due dates, and that's why I was getting emails of people saying that they're due tonight, and I'm going, no, they're not. They're not due till Friday. Well, they were here. So now I've updated it. They're due Friday. However, what am I going to do on Friday? I'm going to transfer the current scores, over to Canvas so we can kind of see because Canvas is where the official grade's kept. You can kind of see where you're at. That's not a final grade. It's just an in-progress grade. The other thing I'm going to do is I'm going to move it from September 1st to the date of the exam. So you will have all the way up to the exam to do all the homework assignments. Hopefully you're starting them and getting a good chunk done. But there may be one or two or a few of them that maybe are holding you back. I don't want you to rush through them. I want you to take the time. And sometimes in learning math, this is what I found, is by moving forward, you actually understand the stuff that came before. But if you never move forward, it's like you could spend eternity looking at it and you just don't understand it. You move forward, oh, it was that simple thing that you couldn't see when you were stuck in here, right? So I want to give you that freedom too. So the due dates will always roll, and even the next one. So those, look at the due dates, the first due date as a snooze alarm, right? You want to get up I wanted to get up at 5 a.m. this morning because I went to bed early, but I hit the snooze for another 30 minutes, and I didn't get up till 5:30. That felt good, okay? So these are like a snooze alarm to kind of get you moving, get you starting it, but if you don't finish it, hit that snooze alarm, it'll still be there for you to work on, okay? So I've got those going, but I just let you know that's what's going to happen on Friday, because I don't have any classes then, and that's when I can do a lot of my processing type stuff. But also don't get overstressed that, oh, I got a 0, I got 50%, and I'm still working on it. That's okay. It will get updated again next Friday. That's how I'll do is each week I'll update it. And then after the test, because you'll have till midnight or 11:59 on the day of the test to finish anything up. It's always best if you get it all learned beforehand, but we'll do that, and then I'll do one more update, and that will be sort of the final, but it's never final, because I always figure if you're willing to go back and learn something earlier on or work through the problems, you'll learn something. So we'll work that out if that needs to be worked out. But again, the highest portion of your grade is based on how you do on the exams. So getting things learned before the exam is crucial. And just because of the way we run things, again, it's not that it can't be run a different way, but this is how it's set up, is our department says 70% of the grades have to be from tests. Everyone gets one attempt at a test. You don't get to retake it. And that's how we move forward. But again, talk with me and be with me. The other thing I wanted to show you, I hadn't looked at the ebook in maybe a year or two. I looked at it before. I saw that a lot of this stuff in the ebook is in the PowerPoint slides, which I take from the textbook company, so that's not surprising. The thing I hadn't looked at is there was an update maybe last year, and there's some, at least they're new to me, some new features in the book that I wanted to point out. So we're going to go through 11.1 today, but I'm going to show you some things from 11 or 10.5. This book, because it's an ebook, they're making them more interactive. So it's not just information, like you see here, and you might even recognize this as one of the slides we used. Some of this stuff is, but let me see. Yeah, this is, I think, definitely one of the, part of one of the slides. But what it has is it's got these little places like this that are your turn, where it's actually interactive. So this is going to use this formula, this difference quotient, they call it, quotient because it's dividing and difference because it's subtracting. So and I just really call it the slope formula, because that's all it is. It's a slope formula where they're taking h and making it go to 0, so they're making 2 points become 1, is all that's happening there. But we can do that is see if h is 1, we see that that's a secant line, right? Going from, let's see again, this case it's going from 3 to 4, because h is 1, it's 3 plus 1 is 4, between 3 and 4. So it's getting a secant line, but you can actually come in here and put in 0.1. And then you can calculate it, and now we see it went from having a slope of 10 to having a slope of 8.2. And then, let's put in 0.01, calculate that, and we see we're getting closer and closer to 8. Okay, so I can then come down, okay, so the instantaneous slope at 3 must be 8. So this is helping with the concept of limits, right? And again, maybe you've got it down at this point, but you can check it and go. So this is for some of you I know have been, when you get to the homework, you're trying it out and you're maybe using up the attempts, especially for some of the multiple choice ones, you only get one attempt. Here's a place where you can sort of do some of it, check it out first with no cost, because it's not getting recorded or anything, and play with it, okay? And there were some other places. There's some interactive things in here. So there's some valuable things in here that are in addition to what I use in the lecture, because I can't go through it all. Here's one where you can actually plug in things. You'd have to use your graphing calculator to get a table here, but again, you could do this one. I didn't find it to be as helpful as some of the others. Let me see. There was one. Here's this thing with tangent lines, and I know some of it's, again, you can see some of these I did the slides on. This one's cool. You can actually zoom in. Sometimes you have to move it up a little bit, but I can zoom, and that's that local linearity. So you can kind of have these interactive things. This one was kind of nice because you can actually, again, physically see, we can make H smaller and it moves the points together. So again, some of these interactive things allow you to see exactly what's happening, and sometimes that's the place where it clicks. During the lecture, I might do the same thing, but you've got a lot going on and stuff, and it might not click, but maybe sitting down, looking at it, that will help it to click. Just know that those type of things are in there. The other thing, though, is to watch out for is the textbook contains more than we're going to cover. So you have to look at what did I lecture on. I'm lecturing on everything that should be in the homework, pretty much. Sometimes I miss something, but if there's a major thing, like today there's something in the textbook called L'Hopital's rule, I don't even touch that. So when you go to look at the textbook, just know, he didn't even talk about this. Okay, we're not going to be responsible for that. So that's one of the things. But the things I did go over in lecture, the things that are in the homework, you can come back here and see what they are. If it's not in the homework, don't worry about going through and learning this stuff, okay? And then there was one in here, I couldn't find it yesterday, but it actually has an activity where you can move. And again, I was creating them with Desmos, but there was one in here where you had the graph and you could actually move the tangent line. And maybe it looks like this is some kind of coding. But just the thing is to use the textbook. And again, I sort of ignore it because all my slides are set up, so I know I've got what I need. But there is some good stuff in here. You're also seeing it written. Oh, I know. I got to keep going till I get to the homework. Oh, there. Sorry. Here it is. So this little thing was kind of cool. You can actually move this tangent line, and you see that as you move the point of the tangent line, what's happening to that tangent line. It's going through it at one point, because that's a hard thing unless you've had some experience, because we've got these drawings and you're supposed to visualize where the tangent line is, and some of you are saying, well, how do you know how to draw the tangent line? Look at something like this and you'll kind of see that as it drags along, what's happening to that slope. And this is the difficult part of the course, is that this conceptual part, that the function value is decreasing. Let's see, let me go back. So on this side, so what the function value is actually increasing, right? It's getting higher, but what's happening to the slope, it's actually getting less steep, so it is decreasing. Okay? And so you get some feel for, so there's some tools in here. Again, I've provided some others, but there's tools in here. Okay, so you might get, just as a practice, after you see the lecture, view the lecture, however you do it, get into the homework, maybe you look over the homework, come into here, into the textbook, take a look, maybe there's a good example for something that you were struggling with. The other thing that I almost forgot to get back to is there's a homework section, just like a textbook would have, the exercises. Let me come back here. So when we get into the exercises, though, the odd questions, just like in a regular textbook, a printed textbook, will oftentimes have the answers in the back, right? This one is cool because it has the answers right where the question's asked. So it's asking the question, and here it gives you the answer. You could go through this thing. Again, I would survey what kind of questions we're asking in our homework. You could go through this, look at a similar type question, look at what the answer is, then you kind of know, oh, this is what they're looking for. Do they want units and those kind of things? Sometimes I have to do that because it's not clear to me exactly what do they want when they ask the question. Because they could, sometimes they're wanting something very specific and they don't really say. So you've got all of these where all the odd problems have answers. And sometimes they're a little, but they're all there. Okay, so that's a resource for you. You're paying for it. You have access to it, and it's all online. So use that as well as an additional resource. Okay, and use it as much as you need or as little as you need. Again, this is about you doing what is going to help you be successful. Any questions on? The other thing is if you haven't paid for the course yet, there should be, when you log in, the little box at the top that says you have to pay by this date or something, because they give you 2 weeks. I think it is about to get set up, and then you need to pay, or else they'll take away your access. I don't know if they do it on day one or they give you a few more reminders. You can reactivate it, but at the same time, try to make that payment. On the other people was doing my other class, it was like $77 and something cents to pay for the access, and then you've got it for the rest of the semester. I think they give you a couple options. There's a more expensive option that gives it through like spring semester. You only need it for one semester because you're going to be successful. You're going to finish this up, and then you're going to move on. Okay. So that was that one. And so where we're at today, we're getting into what are called the shortcuts. So 11.1. What I like in this too is, let me open this up. What we've been doing in our travels is like we're crossing a wide river. So that's where we picked up this concept of limits. That's where we picked up the concept of average rate of change using a secant line. Those all sort of tie back to algebra. We were doing algebra and numerical analysis, putting in a calculator, seeing what we get close to. And then we sort of moved using those two things together, using limits on a secant line. We came up with the slope of a tangent line. Okay, so we put those two things together. But you probably struggled a bit. If you didn't, then you've probably done it before. I struggled a lot the first time through trying to understand what a limit was and all this. And on top of that, even when you understand, working with limits is tedious. It's a lot of extra work, and there's a lot of stuff in the technical side of it. So that has been our boat that got us across this river, right? Because I don't know about you, but I can't walk on water. I can swim, but I get tired fast. So I'm glad I was in a boat. Now that we're to the other shore, that's where we're starting now, is we're going to start looking at to get the derivative directly with some shortcuts, some easier ways to get it. Do we need that boat anymore? We're on solid ground. Do we want to carry that boat with us and go hiking through the woods with it? I don't. So we're kind of going to leave limits behind now, because we just use them to kind of prove that this will all work to ourselves. And then what we're going to use now is, it may not seem as concrete, but it does work. Okay? We didn't have you go through the really technical side of using the difference quotient that much. In fact, I don't think we had you do any of the algebra with it. We used to do that. That would take about a week. It'd be very frustrating. That was about the place I was ready to drop out of the course when I went through it the first time. And then you get out of it and you get to these shortcut rules. You go, okay, we don't use them anymore. Okay, I can do this class. But I was thinking, if this is the way the rest of the class is going to go, I got to get out of this thing, right? Well, we took those away because they were only a technique to get us somewhere. So now we're going to go here. If you can subtract 1, how many of you feel pretty confident subtracting 1? 2 minus 1 is 1. Okay, good. You're a good. Okay, so if you can do that, we're good. 3 minus 1 is, okay, we're in a good place. That's all we're going to have to do. And then we can multiply by smaller numbers. Sometimes we have to do bigger numbers. We can use our calculator for that. But that's all we're going to do to get a derivative. And it's, again, we didn't go through the process to show that this works, but part of what I do is, when I was learning math, is I had faith that the people who went before me that did this book, they spent the time and they got there. And a lot of the stuff we've got in our textbooks, it took 300 to 500 years for people working on it to actually figure it out. But there's at least 2 different ways of learning. The 2 main ways: we can learn by ourselves from our own experience, and that's helpful. But we can also learn from other people's experience. And when we put those 2 together, we can go a lot further. So we don't have to reinvent everything. We can take what other people have done. And that's what we're going to do today, is just remember, it seems too easy. All I'm doing is subtracting 1 and multiplying, or multiplying and then subtracting 1. That is it. But it's based on other people that went before us who really spent years and years of their lives to research to say that this does work. It gives us what we want. And we're just kind of going to pick it up. Okay? So we're going to talk about derivatives, and we're going to focus on just a few parts. Powers, so these are exponents, so x to some power. That's the only type of derivative we're going to talk about today. Later on, we talk about derivatives of other types of functions like logarithms and exponentials, but we're just talking about x to some power. And we're going to get some shortcut rules. How many of you like shortcuts? I love shortcuts, especially in traffic, right? Go around and it took you 5 minutes instead of an hour to get through things. Were any of you caught in the 101 backup? Yesterday there was like the police did a maneuver and a car spun out and trying to get away and caused this big accident, and I guess it was backed up. I-5 or 101 North. So here's the justification for what we're doing, for leaving that boat behind, is that even the book says, this is a quote from the book, the calculation of a derivative using the limit is tedious. These are mathematicians even saying that. They even find it tedious. So we're going to leave it behind, because as what we're really focused on is, right, taking data or whatever's happened, using the math to make good business decisions, or whatever field we're in, but computing decisions, whatever field you're in. And if the process of getting that derivative, that rate of change, is very tedious, we lose track of what we're trying to do. If we can get some simpler technical methods, we can focus more on the problem and on that decision that we need to make. Do I buy or do I sell, right? Sometimes that's as simple as that. And if it's all this technical thing to do this, then I forgot, what am I even trying to do anymore, right? But we're going to break it down. That will make it easier to do the calculations, and then we can just make our decision. It'll hopefully become clear. So here's the first thing we're going to look at. It's a simple, beautiful rule, but it has some technical, so we'll go through it. So here's the idea. Okay, we start with a function. So here's f of x, some function. Whoops, I forget to do this. I have to turn on my pencil. There we go. Okay, so we start with a function, and then we're going to take its derivative. What's the difference between the output of a function and the output of its derivative? Help you a little bit. The output of a function gives us a value. So if it's a profit function, the output is the profit itself. What does the derivative give us? The slope of the tangent line, right? What is a slope? It's a rate of change. So it gives us how the profit is changing. So this is the key concept you want to pick up from this course, and it will take time. The function gives us a value, profit value, cost value, whatever the application is, right? So that gives us a value, an amount, what the cost is, what the profit is. The derivative always gets us how it is changing. So some of these examples we'll see the value, the function value is like 1,400. It's way up there. Maybe that's dollars or something. The derivative might be 5. That means it's changing by $5 per hour. But we're at 1,400, so we could see the next one is going to be 1,405 is the way we can kind of think of it. So that derivative is giving us the change. The function is giving us the value. And throughout the course, you'll be going back and forth. You'll be using both the function and its derivative, because sometimes we want to know what it's changing, how it's changing. Sometimes we want to know what it is, right? Where are we? What is the price of gold right now? Boom, I use the function. How is the price of gold changing? Boom, I use the derivative. Okay. So notice this though. If my function was x squared, the derivative is 2x. If the function is x to the third, the derivative is 3x squared. What does it look like is going on here? Well, it certainly looks like they're just taking the exponent, they're moving it down in front, 1 times 2 is 2, and then they're subtracting 1 from the exponent. 2 minus 1 is 1. Oh, that worked there. The second one, if we took this exponent of 3, moved it down in front and multiplied, 1 times 3 is 3, oh, there it is. And then if I subtract 1 from it, 3 minus 1 is 2. And that's exactly what's happening. In fact, they call it the power rule. If I have any function that is x to some power, and they're using the letter n, it doesn't have to be an integer or a positive integer. It could be a negative value. We'll do some of those. It could be a fractional value, as in the case of square roots and stuff. But whatever it is, the way to take its derivative is simply to take that exponent, bring it down in front, and multiply by the number in front. And remember, if you have x to the n, there is actually a 1x to the n there. So 1 times n is n, and we just subtract 1 from the exponent. That's all we're going to need to do to get our derivative as a function. And then whenever we want to know what is the derivative at 3, we just plug in 3 to the derivative function and we'll get it. No more limits. Throw that boat away. We don't need it. We're going cross country now. No more water, hopefully. If we hit the swamps, we'll put on hip waders or something. But this is all we're going to need to be able to do. Again, we'll look at some examples because it does get a little bit. It can, the calculations, we may have to do a fractional exponent. We may have to do a few things, but again, quick example: x squared. Bring the 2 down. Subtract 1 from the exponent, so we get x to the 1, and then we're just rewriting it. Now, this is sometimes the hardest part to do is just x to, because it does, if it's x to the first power, they don't write it usually, right? And so then we're looking at that. That's just there is no exponent. Yes, there is. There's always a 1, but they make it invisible to save some ink or something. I don't know why they do it, but there's no problem with keep writing the 1. And as you'll see when I do work through these, when there is that x to supposedly no power, I will write 1 because I need that 1 there, because what am I going to do with it? When I take its derivative, I'm going to subtract 1. So we're going to one of the things, the algebraic part we're going to do is when we are given a function, we write everything as x to some power, and then we can take its derivative. Okay, so here's some examples. A, it's not x to some power yet, is it? It's 1 over x. But how would I rewrite that as x to some power? X to the negative 1. X to the negative first. Good. Because that's, hopefully you remember from algebra, that's a reciprocal. So whenever I have a fraction, move it from the one book I called it an elevator rule. So I'm moving it from the basement to the first floor, but to do that I have to put that negative 1 exponent, because that's saying actually this thing belongs in the basement. You've got it upstairs, but you need to have the negative 1. However you want to look at it. Now how do I take this derivative? Last time I just take whatever that exponent is and I multiply it by the number in front, which in this case is a 1. So I get 1 times negative 1. What else do I do? I subtract 1 from the exponent. Negative 1 minus 1 is negative 2. So that's, again, there's another one. A lot of us will look at that and say that's 0, because we forget how to subtract negatives. When you've got two negatives, you actually end up adding them. So we call it subtraction, but it actually, 2 negatives, you're actually adding them together and keeping the sign. So this will be to the negative 2 power. And so the way we end up writing this, 1 times negative 1 is negative 1, is we rewrite it as negative 1. We take the elevator back down and say you really belong down here, so let's do this with a positive exponent. Now, there's nothing wrong with writing x to the negative 2. However, sometimes in textbooks and homework systems, they will say, write your answers with positive exponents. So it will mark it wrong when it's not really wrong, it's just not in the same form they want, right? And a lot of you have had that experience. They wanted it as a fraction. Sometimes they don't tell you that, and you put in the decimal and it keeps marking it wrong. You weren't really wrong. It was the system wanted something different, and they didn't tell us. So, again, I always think in circles, and when we get to the homework, remember what I do on the scores. If you have 90% or above, I'm going to give you full credit, which is actually 105%, because that assumes you've got it done on time as well. If you're below that 90% and you got some things, individual questions like that, where you were really putting in the right answer, but it wanted a fraction, or something. If there's some problems, after the exam, I'll take appeals for individual scores. We won't do it as we go because, again, there's that opportunity to change. But even if you get locked out of something, just keep track of what you're doing. As long as you can let me know, you can convince yourself that you understand first, then you'll be able to easily convince me that you understand, and that was just sort of a technical issue. I don't want you losing points because of technical things. Okay, so we'll have that opportunity as we go through. Okay, so just remember, we'll do that. So 90 and above, we don't worry about it because I know there's some things that you're not going to get full credit for that you should have. So usually it's a small thing, but if it's more and you're only getting 80% and you really should have got 100%, we'll talk about those after. Okay. Okay, how about this one? B. What is this really? How should we write this one? Excellent. So we just put it on the elevator, move it up, the positive 2 becomes a negative 2, and now we can take its derivative. Now some of you will look at these and you'll be able to do the derivative without doing that step, because mentally you'll do it. I still have problems with that because I go the wrong way. I'll take 2 minus 1, I'll get 1, but it's actually negative 2 minus 1, and I need to see it. Otherwise, I go the wrong way. And again, the other thing I forget to do is that when I go to multiply, what I'm multiplying by is a negative 2, right? If I don't do this step, I multiply by positive 2, and I get my negatives off, and I go the wrong way. So, and I've got 24 years of getting paid to do this stuff, and I still make mistakes. So, but some of you have a different approach to things, and the way you think of it, you'll do it just fine. And maybe doing this extra step is what causes the problem. So we're all different, but we find the ways that work for us. So I bring the negative 2 down, multiply by 1, got my negative 2, and then I subtract 2 from, I subtract 1 from negative 2. See, I can't even speak about it. So negative 2 minus 1 is negative 3. This is where it kind of feels that because it seems like the exponent is getting bigger, it's actually getting more negative, which makes it smaller. So it is happening. But when we're dealing with positive exponents, we get so used to, okay, 4 minus 1 is 3. We get that it's, the number's getting smaller. Here, when we've got negative, the value gets actually larger. I went from 2 to 3, but I was negative 2 to negative 3. So, and again, if they ask, now there's nothing wrong with this answer as it is. However, if they say in there somehow we want it as a positive exponent, then what they're looking for is to have the 2 stays on top. Now, when it takes, or actually the negative 2, when we go on the elevator, only the negative exponent goes down. So that's another thing else I'll see. Some people will put that negative 2 down into the denominator as well. Negative 2 it doesn't have, actually, it has an exponent. It has an exponent of positive 1, if you want to think of it. Okay, so that would be our answer with positive exponents. Okay, so again, we kind of put it on the elevator so we can work with it. We get done, we got a negative exponent, put it back on the elevator so it's positive, and we're all good. But again, all we're doing, multiplying by the exponent and then subtracting 1 from the exponent. That's all today's lesson is. we're going to, again, gets a little complicated. So C, this is where, so how do I rewrite a square root as x to some power? Good, 1/2. Or 0.5 if you want, but we'll go with 1/2. So now I have it as x to some power. What do I do with that power, with that exponent? I bring it down and multiply. All right, so I'm just going to circle it. It comes down. 1/2 times 1 is 1/2. And then what I have to do, though, this is sometimes where, because I've got a fraction, I have to subtract 1 from this fraction. Make it a little easier. There are multiple ways to write 1. Right? Remember, with fractions, we need a common denominator. So we need 1 written as something. How many halves is 1? So remember, I can always write 1 as a fraction, 2 over 2, 3 over 3, 4 over 4, 5 over 5, 27 over 27. Those are all different ways to write 1. So I'm kind of going to do it up here. So when I have 1/2, what I want to do is I want to subtract 2 over 2. Just go straight to that, right? Don't write 1 and I got to get a common denominator. That's an extra step. Write your 1 as in terms of the common denominator. Whatever the denominator is, put that as that over that, right? 5 over 5, 2 over 2. And then the arithmetic's so much easier. So when we're subtracting with the common denominator, the denominator stays the same because it's really counting. We've got 1/2 and we're going to subtract 2 halves from that 1/2. 1 minus 2 is -1. Okay? So this will make working with fractions much easier. And again, we don't do it a lot, but occasionally we will. And that's the thing, is sometimes when we don't do things a lot of times, we don't get real proficient at them, and it's kind of like a struggle each time. So this is a way to take some of the struggle out of it. So our exponent is now going to be -1/2. Okay? And again, it's a perfectly fine answer as it is. However, they may want it with a positive exponent, right? Sometimes, since it's a fractional exponent, they may want us to rewrite it with a radical. So you may see it that way. Sometimes they'll accept either one. But another way to write this, now notice the 1/2 doesn't have the negative exponent. It stays 1/2. The 2 stays in the denominator, in the basement, right? Technically, the x is up in the numerator, because it's with this. We're going to move it down to the basement, put it to the 1/2 power, the positive 1/2, and I'll rewrite the positive 1/2 as a square root. Okay, so you will oftentimes, in most textbooks, you'll see the answer written this way. Again, the online homework may accept this first form of it because it is correct. It's just there's different ways we write things, but it's symbolically different. And some, our brain doesn't always, again, depends on how often you see these things. So sometimes it looks very different. And you're going, how did they do that? Well, this translation. It's really speaking 2 different languages, right? So those of you who speak more than one language fluently, you probably have an easier time looking at these symbols. I've studied other language, but I'm barely fluent with English, so I would like to, the experience I really would like is I've heard people who study a language deeply, they can actually dream in that language. I have sometimes had dreams in Thai language because my adopted brother is Thai, so since 15 I've been around that language. But I never understand what's going on in my dreams. I'd like to be able to understand sometimes, and my brother says, when I get drunk, when I used to get drunk, I actually would sleep. I'd sing in Thai when I was sleeping. So it's kind of sometimes when you sleep, your brain does more things than you're awake. Your consciousness says, I don't know Thai, so I can't do that. But there's kind of sometimes you unlock certain things. Okay, enough of that. So that's really all we're doing today. The rest of this is going to be a few things about some other notation. Again, the way calculus was developed, actually, it was developed many thousands of years ago, but the European development of it that we see in our textbooks England, some guy named Sir Isaac Newton had an apple fall on his head, so he gave us gravity. He also gave us stuff for calculus. I believe the notation we've been using as F prime, that's his notation. There was some other guy at about the same time called Leibniz. I can't remember if he's French or German, does anyone know that Leibniz, would that be a German? Okay, I was thinking it was German, but some of this math, so the big math world, at least during the European times, was England, France, and Germany. And yeah, I was thinking so at the same time, the Germans are developing symbols for what they were just discovering as calculus. So in the textbooks, you'll see both of them, different symbols, remembering they were also in different languages, so that had to be translated, but oftentimes the math symbols didn't get translated. So here's a different notation that we're going to use. So what I do is I got very comfortable with this, what I call the prime, F prime, that's the derivative. But we're going to see, they're going to, in Germany, the derivative of x to the third, so they're going to write this as the derivative with respect to x. So they use this as a symbol instead of x prime. Because what they did is they didn't use the function notation as much, so they would just say, well, we got this function x to the third. If I want its derivative, I would do d over dx. So don't try to understand, is that a fraction or what? It's just a symbol that's saying take the derivative. We get a little bit further, but also it works well if we're doing multiple variables. Like if we had x, y, z, we might be taking the derivative of one of the variables, and so this gives us a way to figure that out. In this class, we don't go there. In the engineering version of it, they do. So sometimes this notation actually works better for us. So the thing you just need to be able to see is when you see this d dx, that that just means take the derivative. What I did the first time I went through, if I saw something like this, I just, they want the derivative of x, and I would drop off this stuff. Okay, so I just translate it and go. Some of you, maybe you're more comfortable if you've had a course before and that's what your instructor used was d dx. If you're more comfortable with that than the prime, you could use that. So again, they're just different ways of saying, hey, give me the derivative. How do we get the derivative? Again, it's all the same process. Take the exponent, multiply, and subtract 1 from the exponent. So that's all the same. Doesn't depend. When they have a variable involved, oftentimes they'll do it as dy dx, so we're taking the derivative of some function that has a y, the output is y, but we're taking the derivative of the input of x. So you'll see that. Again, I just find it easier to say, let's do this. Okay, so you can, again, don't get too heavy into the symbols, but when you see a homework problem that asks it in that way, just say, that's all it's asking is for me to take the derivative. And at this point, all it is take that exponent, bring it down, multiply, subtract 1. So we see this one, again, the same thing, x to the third, the 3 comes down, subtract 1 from it, we have the derivative as 3x squared. Okay, so the function itself is a cubic function, right? And we'll start to see this cubic function, x to the third, if you graph it, looks something like that. What does 3x squared look like? It's a quadratic function. So you'll see that as we do things, the derivative is sort of one step down. So a cubic function becomes a quadratic becomes a linear becomes a constant. X to the fifth power, its derivative is going to be an x to the fourth, some kind of x to the fourth power. So we're losing basically 1 power. And again, the thing is when we use the derivative function, what do we get? Slope of the tangent line. Okay. If we use the original function, what do we get? We get a value, a profit, a cost, something, miles, how many miles we've traveled. The derivative gives us how many miles per hour we're traveling. Okay, so value versus a rate. So now we're going to get into, it'd be a pretty boring world if all we had was x to a power and that was it, right? X to the fifth, that's it. So what about multiples? And so if we're adding or subtracting things, what we're going to see is the sum rule. Don't get too put off by the symbols. It just means if we had x to the fifth plus x to the third minus x squared, that we can take the derivative term by term. That's all it's saying. So if I have this one with 3 terms in it, when I go to take its derivative, and I'll do it this way, I'll use the new notation. I'm going to take its derivative. It's simply going to become x to the fifth becomes what? 5x to the fourth. Good. Because see, again, learning theory, when you say it, I mean, you can think it, and I've done this with learning languages. You just say it in your mind, but you have to actually verbalize it, because then that's using more of your brain to move that tongue and everything else. And then x to the third becomes 3x squared. Okay, so bring the exponent down, multiply, subtract 1 from the exponent. That's all we're doing. Negative x squared becomes negative 2x to the first power. I'm going to write that first power just to emphasize that's what happened. Because if you see nothing there, sometimes your brain's going, well, what's there? Okay. We good so far? Okay. So it's sort of intuitive, at least for me it was. Again, mathematically, they never make any assumptions, and sometimes intuitive things don't work. Sometimes we have these rules where we got a fraction, anyway, sometimes we make our own rules. So it's good that what I do is I say, well, some mathematicians spent hundreds of years proving that works, so I'll just take I'm going to learn from them and move forward. Okay. Constant multiple rule. So if we have something times a function, it's something times the derivative. And we could do that with just a simple one. So if I had x to the fifth, if I had, say, 3x to the fifth, that 3 is a constant multiplier. And so what I technically do is I just put the 3 on the outside, sort of take the derivative of the inside. So I bring the 5 down. I put x to the fourth, right, subtracting 1 from it. And then I just multiply by the 3. But in reality, I just get used to, I bring that 5 down, and that's why I said I take that 5 times 1. And so if there's a 3 there, I just take the 5 times the 3. I don't do this intermediate step. I don't even think about the constant multiplier rule because I incorporate it into how I learned it. This is now just 15x to the fourth. So that's what its derivative is. And again, I'll put the little symbol that I'm taking the derivative of 3x to the fifth. Okay, so constant multiplier rule, again, fairly intuitive for me because I'm thinking I'm just taking this exponent, multiplying whatever's in front. There's your constant multiplier rule. So I don't really use it as a rule. It's natural. I don't really use the sum rule or the difference rule. If I'm adding or subtracting, I just do it term by term, and that seems to make sense to me. Okay, we're going to get some rules next week, product rules if we're multiplying two functions that are kind of like the FOIL rule for algebra. It's a little more complicated than that. The quotient rule, when we're dividing two functions, it has some more complications, so there's time for that. But if we just have a simple polynomial, things that are being added together, we just do it term by term, and it works out perfectly. Okay, and this is just, again, a slide, because the textbook does use both, using a different notation, but it's the same thing. So again, what I'd like you to do is to see those so that they don't scare you. What's this stuff? Well, it's just a different notation, but you can translate and you can figure out which one is more comfortable for you. Again, you might be more comfortable with the prime notation because I'm more comfortable and I use it more often. This stuff becomes a technique that works later on. So we introduce it now, and just understand it was two different languages. So it was the English language, German language, two different people coming up, making up some sort of symbols that work. And so each has their benefits, each has their drawbacks, but they're just the same thing. So here again, just with the same old notation, or the new notation, the one I don't really like, I'm not as comfortable with. But it just says take the derivative, so you take term by term. So x squared is the 2 comes down, and we get 2x to the first power. And again, I always like to write those exponents because that's what's happening. And then x to the fourth becomes the 4 comes down, x to the third. The other thing let me get some. I'll give you some insight to where we're going in this class. This is pretty much going to take us halfway through the class. First half of the class, we're doing derivatives. A few extra rules we'll get in here to do it, but if we get this down, this is the foundation, this is the building block of doing derivatives from here on in. The second half of this class is called integration. I also like to call it underivatives. So we start with the derivative and we want to get back to the function. We're doing the same thing, but we're going backwards. So instead of subtracting one, we're adding one. Instead of multiplying, we're dividing. So it's sort of an inverse. So as you go through this, spend the time to kind of get detail, look at what you're doing, reflect on what you're doing, and get comfortable with what you're doing. Sort of think of this as the forward way. Because the second half of the class, we're going to basically take this, we're going to start at the end and go backwards. And that's always a harder journey, right? A lot of us can FOIL out algebraic, x plus 5 times x minus 3. We can FOIL that out, but when we've got the answer, going back and factoring it is harder. But if you understand the forward operation, going backwards can be easier. But there's sometimes it's a little bit of a puzzle because there's stuff that happened in the middle that we have to remember is going to happen when we go backwards. Okay, you take apart an engine, it's pretty easy. I've done it. Put it back together, and there's all these extra parts. Well, where did those go? Oh, forgot to. Hopefully it still works. It ran for about a week. I guess it needed those extra parts, but hey, it was fun. Okay, so yeah, going back the other way is harder, but we're going to go there. So as you do this, just kind of keep that in mind, that I want to understand this forward process so that when I go backwards, I remember those little pieces that sort of disappear as I go through. Okay. And forwards and backwards. And then that's the end of this class. So again, as long as you can add and subtract by 1, you're in really good shape. And multiply. Okay, so here's one. Find the derivative of this, right? And this is one place. I'll take a little pause, so if you can maybe in your notes kind of go ahead and try to do that. I'll take a drink of water. And then I'll talk about it, right? 3x squared, 2 times 3 is 6. 2 minus 1 is 1. This middle term, there's a 1 here, so 1 times 2 is still 2. 1 minus 1 is x to the 0. What about negative 4? Did anyone get stuck there? We never talked about that, right? Doesn't have an x. Doesn't have a power. Let's remember what we're getting. So this is a little bit of, we kind of go off to the side. What do we do when we have just a number? What is just a number? So again, we're bringing this down in pieces. What is the function y equals negative 4? What does that look like? It's a horizontal line at y equals negative 4. What is the slope of a horizontal line? 0, because the y value never changes, so you're taking 2 minus 2, or in this case, negative 4 minus negative 4 in the top. Its slope is 0. What is the derivative? It's a slope of a tangent line. So if the slope is 0, the derivative is 0. So that's the one thing. Whenever we have a number without an x, right, its derivative is going to be 0. And so that's one of the things. So it's sort of simple because that's what it always is, but it's also difficult because it's hard to, I can't show you the rule. It doesn't apply to this power rule thing, right? There's no x. I can't I can't manipulate it. I just have to remember it. The other thing is this 2x to the 0. What is it going to become? What is anything to the 0 power? 5 to the 0 power is 1. 27 million to the 0 power is 1. So when we have it to the 0 power, that's 1. Now the one thing that isn't is 0 to the 0 power. So that causes some problems, but we'll skip past that. So this actually becomes 6x plus 2, and that's our final answer. Notice the constant disappeared. It became 0. The 2x to the first power just becomes 2. The other way to think of this is, what is 2x? Y equals 2x. It's a line, right, that goes like this. It's got a slope of 2, and everywhere on that line it's got a slope of 2. Any 2 points you're going to get a slope of 2. That's because it's a linear equation. So remembering the derivative is the slope. That's why it's a constant slope of 2. Now this one's 6x, the slope will change, right? Because we've got an x squared, so that's where that all comes in. So this is our final derivative. But again, sometimes these can be the easiest part because, okay, I don't really do too much, but that also makes them the harder part because we don't have a gut level understanding of it. It seems to be something outside of bring the exponent down, multiply, and subtract 1. Right? It's different. But so those are the two things we need to get comfortable with. Everything else, just take the exponent, bring it down, multiply, subtract 1. But those are the two exceptions. So far, so good? Making sense? And again, if you go into the textbook, the ebook, they had this problem where they have about 5 or 6 of these where you can do it and check it, and it will tell you whether you're right or wrong. And again, you might be missing some of it. And again, it doesn't take, those are unlimited, and it's not going to penalize you in any way. It's not going to take away your tries. So let's look at this one, which is a little bit more complicated. And again, I kind of went, hopefully, further out in a stream than maybe we're going to have to do, but we'll see. So again, what we want to do is, we're going to do algebra first. We're just going to rewrite the function. We're not going to take its derivative just yet. We're going to rewrite each one of these as some number times x to some exponent. Okay? So this first one, 2x over 3, what does that really become? It's really 2/3 is the number that's getting multiplied by x to the first power. Okay, so notice me, I will go ahead and with no power on, I always put that 1. I always want to write what that exponent is. Negative 6 over x becomes what? 6x to the minus 1. So the x goes on the elevator, becomes a negative exponent. The 6 stays where it's at because it's a number. Okay, so that's part of this. When we work with fractions, some of us, maybe it's a little bit harder. Okay, 2/3, excuse me. I get my 2/3. And then again, I'm going to use that x, I'm going to move it upstairs to the numerator by making a negative exponent. And it's a decimal exponent. It's a nice decimal. You could turn it into negative 1/5, but depending upon whether you want, we'll kind of do it both ways, and we'll see how that all works. But we'll leave it at 0.2 for now, because we could. And then how about this x to the 4th over 2? So I move that 2 up. No, it's in the denominator. It needs to stay there. So this is really minus 1/2 x to the 4th. Okay. So see how if I rewrite everything as some number times x to some power, then all I got to do is follow the power rule. Take the exponent down, multiply it in front. And again, sometimes the arithmetic is a little more complicated if I've got fractions. And then I subtract 1 from the exponent. That's all I'm doing, term by term by term. So now I'll go ahead and step by step take this derivative. And again, we're spending a methodical time going through this because this is the foundation to everything else. Once we get this down, everything else, but then what we're going to do is add a few extra dance moves that are a little bit more complicated, but we need these. Anyone do salsa dancing? No, Oregon, it was real big. I tried, and they said there's this sort of thing that you're supposed to like brush your teeth while you're doing it. You just get this basic salsa move, and then you're actually able to do. I did a little bit, and I wasn't really good, but I could see how you need that basic sort of salsa move. That's what this is. If you got this down, the rest of the stuff we're going to do, you're going to be able to do spins and twirls and all sorts of funky stuff. So this first part, right? The 1 comes down. What's 1 times 2/3? It's still 2/3. Okay, so I love multiplying by 1. And then what do we do with the exponent? Subtract 1. I'm going to write it as x to the 0. You could choose to not write it down if that's helpful for you, because it's going to go away, right? X to the 0 is 1, so it's just going to be 2/3. That's okay. I look over here before I put the negative, right? I'm going to have a -1 come down. -1 times -6. +6. And then I'm going to subtract 1. -2. And again, next step, I'll move it underneath. You don't necessarily have to show all these steps or do all these steps. Again, do what works for you, but also recognize that's what I did. Is sometimes I need to do these middle steps, because if I don't, I get the negatives off, or I'm not doing the arithmetic correctly. Okay, so we're good so far. Now we've got this number here, -0.2 times 1/3, or sorry, 2/3. I'm just going to write 2/3 times -0.2, and I'm going to deal with it later. Okay, sometimes I know the process, but I know that's kind of complicated for me, so I'm just going to leave it as is. And then this part I can do, -0.2 minus 1 is -1.2. Okay, so that's just the arithmetic with exponents. And then this last part, the 4 is going to come down. I will do this 1/2 times 4 a little bit, right? 2 goes into 4. So this is just going to become 2, so that's a little, so it's going to become -2, the 4 times 1/2, half of 4. And then I'm going to subtract 1 from the exponent, so that's going to be to the 3rd. So that one wasn't too bad. But again, working with fractions and such. We'll clean this up. Again, it's a correct answer, but not completely worked out. So this first part is just 2/3. X to the 0 is 1, so 1 times 2/3 is 2/3. This part we'll rewrite as +6 is in the numerator, x squared is in the denominator. So we put it on the elevator, moved it down, turned the negative exponent to a positive exponent. Again, sometimes they ask for it specifically to be with positive exponents. If they don't, we could leave it with a negative. This one is, okay, 2/3 times -0.2. It's going to be funky because I can see I'm going to get a decimal in the numerator. It would be 0.4, -0.4, 2 times 0.2, right? And that's kind of funky, but I'd have divided by 3. So it's a decimal and a fraction. So you could do it either way, or you could take 2/3 times 0.2, but as we've experienced, that gives a sort of a repeating decimal, because 2/3 is 0.666666 forever. How many decimals do we use? The other way, you could think that 0.2 is also 1/5. And I'm not sure that there's one like this in the homework. I just wanted to do one that was kind of a little bit extreme. Sorry. 2/3, if you look at 0.2 as 1/5, you could do it this way, and so that's going to, let me go down here, that's going to give us -2/15. Okay, so you could write that as a fraction. You could also write it as a decimal. It would be correct, but it's going from positive to negative, and just for sakes, I'll do 2/15. I'm going to leave the -1. What do I want to do? That x goes down into the denominator, and I make the 1.2 positive. So I take a negative, move it down to the basement. That's all I did. But I'm just going to leave it as 1.2. And then -2 x to the 3rd. Did I mess up? Question? Because sometimes I make mistakes. Don't think, oh, he's never makes mistakes. I make mistakes all the time. Sometimes I do it on purpose, but I usually don't have to do that. I just make them naturally. And so if you catch it, let me know because I like to get it fixed. Monday's lecture, I made some kind of, I forgot a negative sign or something. Okay? So that's our derivative, step by step. I think that's, let's see, do I have anything more? Just a couple rules again, and this is just with the new notation. So we have some number times x, the derivative is just going to be that number, right? We talked about that's because it becomes x to the 0, which is just 1. So that might be the way you want to remember it. We have a constant, which is a number. Derivative of a number is always going to be 0 because that's really a horizontal line, slope is 0. Okay, and a couple quick examples there. We do have an application. Let me go ahead and go through this. It'll probably take about 5 minutes. So we'll see it. So we could read through this. It tells us we have a stone thrown at 104 feet per second. It's a height of 1,200 feet. But the cool part is they give us the formula right here. And the question is simply to compute the derivative of the function they gave us. So what I found is, being dyslexic, is I sort of read questions backwards. I look at what are they asking, and I sort of read it from the bottom to the top. Because if you start reading at the top, you might start thinking, I got to set this thing up, and you might start either being stressed or worrying about it. We don't even have to know that. They could have left that first sentence out, right? And we'd be fine. We've got the function, and they just want the derivative of the function. However, if we come back and read it secondly, then at least we've got a context, right? A stone is being thrown. Shouldn't throw stones, especially from 1,200 feet. You might hit somebody, right? But we can see 104 feet per second, so we can see that part there. We see the 1,200 here. So we can understand what this function's sort of doing. But we want its derivative. So the function is the height of the stone. That's a location of the stone. When we take its derivative, what is the derivative going to give us? It's going to give us a rate, feet per second. It's going to give us the speed of the stone. So this is nice because it starts to give us a context. The first function gives us how high the stone is from being thrown down. We can get its height. The derivative is going to give us how fast that stone is traveling. So all we have to do here is the same thing we've been doing. So what's the derivative of a constant? 0. 1,200, its derivative. I'm going to go ahead and write zeros so that in my mind, I see I took that derivative. I didn't just drop it. It just didn't disappear. It's just that it's 0. What's the derivative of the middle term? Negative 104t. Negative 104. And again, you'll get to the place where you don't put t to the 0. You could put t to the 0, but soon you'll see, okay, anything with just t or x to the 1 power just goes away. And then what's the derivative of the last part? 2 comes down. What's 2 times 16? 32. Negative 32, because there was that negative. And then 2 minus 1 is 1, so it would be to the 1 power. Again, we don't have to write it. So the first part of this question, the derivative is simply negative 104 minus 32t. Again, remember, this derivative is going to give us the speed of that stone that we threw. The original function would give us where it is, where it is. Okay. The second part of this question, and I don't know if they still have it in the homework. This was from the homework when I did this. I'm not sure if it's still there. Is that then it asks us to find the stone's velocity at various places. This is where we start to see, if we had to do limits, there would be a lot of work to do here, right? We'd be looking how it's changing and we'd have to do a lot of calculations for each of these. But what we get to do here, and this is where I'm going to introduce the graphing calculator, which I got a new subscription, and hopefully it opens nicely for us. Last time when I tried to do this, it keeps asking for me to sign in. Okay, maybe it's going to work. Oh, no, it's not. Anyway, I'm going to bring in, how many of you have a TI 84 calculator or 83? Okay, a number of you. Some of you might have some other. Actually, you'll see it's in here. So remember the last thing I did. I'm gonna turn this one off. Okay, so all I have to do is put the function in. So this is the derivative function that I created, or I calculated, and then to get all my answers, I just go to the table, and the table they wanted at time 0, it's going 104 feet per second. It's negative means it's going down. That's when I first threw it, and then it's picking up speed because of gravity. But then notice I can just basically copy all of these over for the speed, right? I can put them, I can just fill in the table here. The last question asks, when does the stone reach the ground and how fast is it traveling? So when the stone reaches the ground, how do we find that? That's our original function, right? Oops, where is it? And that's why, if I go back to y equals, I have my original function here. Now, I had to also get the window so that it would fit there nicely. If you have struggle with that, I'd be happy to talk with you. But when I graph it, what I do is I see it's hitting the ground when y equals 0, right? That's the ground is y equals 0. And that's 1, 2, 3, 4, 5, 6. If I wanted to, I could go to the table, and I see that my second function is 0 when time is 6. After 6 seconds, it's hit the ground. How fast is it going? It's going 296 feet per second. The negative means it's going down. So now I can come back and I can answer this part. The stone is traveling at a velocity of 296 feet per second when it hits the ground. Now I think in that one you don't want the negative, it just wants the speed. It may want it because velocity also has direction. Again, that's why we give you multiple attempts, but notice how I can take that derivative. And what we have now is we have the power to work with a function and its derivative directly. And notice how quickly I can just graph them both. I can look at a table of values. The key part I have to do is I have to remember when I'm working with the derivative, I have a rate. In this case, I have a speed. I have how things are changing. When I have the original function, I have the value. Where is it in this case? So I have to keep track of those two different things, but I get quick access to both of those side by side. And that's the power we're going to build as we go through this. And again, from this point on, this is our foundation. We're then going to add some other rules to take some more complicated derivatives, but it's all based upon being able to kind of seamlessly take the power down, multiply, and subtract 1. So with that, that's our salsa step. That's kind of what we're going to be doing day in and day out, and then we're going to add some other things to it. All right? Have a wonderful weekend. If you have a class on Monday, don't come. It's a holiday. 4-day weekend for us.